That voice is very low. All right, let me turn it down just a bit. Okay. All right, so if I take a look at some of your sample answers here um, on the um, one from Thursday, which is simply to work through which one of these combinations, or I should say which ones of these combinations will make a solid. It'll be insoluble. It'll have a very low solubility. And then for at least, I should say, for one of those combinations, what's your source? Then I see a lot of people are still missing things that do in fact make precipitates. So you do have to check out all of the combinations. So when you have like sodium carbonate, you have to combine carbonate with the cation of all 6 of those and see what happens. What happens if you get silver carbonate? What happens if you have lead 2 carbonate? What happens if you have calcium carbonate? What happens if you have iron 2 carbonate? What happens if you have magnesium carbonate? And finally, what happens if you have copper 2 carbonate? Which ones will be solid and which ones will be dissolved? And then the second thing, we then go to sodium phosphate. All right, so silver phosphate, lead 2 phosphate, calcium phosphate, all the way along. You have to plow through these in order to find out which ones will be solid and which ones won't. And then after you've done those 4, then you can really answer the other questions, which anion or anions precipitated most often. Was it the carbonate, the phosphate, the hydroxide, or the sulfate? And which cations tended to precipitate the most often? Was it silver, lead 2, calcium, iron 3, magnesium, or copper 2? So, and those are multiple choices. So do be sure to answer those according to your best research. Okay. Questions about that? Thursday's thing. I'll ask you that again. Questions about that? Okay, Ariel says no. Great, we can move on then. All right. Thank you, Kayleen. All right. Okay, so the thing on Friday that I then said, based on what you found out on Thursday, what are some names? What are some names of those things you're dealing with? And as you look at those, I anticipated people would name the reactants, the reagents, but some people decided to do the products, and that's fine. That's fine. Just need to give 2, and all the way down the line, as well as resubmit which ones do make precipitates. And if for some reason you are more correct on the Friday one, then I will, about those 6 possible combinations times 4. Then I will go ahead and raise the grade from the Thursday thing. But it's building on that. So what are those names? So um, let's see here. On those names, um, I am seeing some good things, but there are a couple of things that aren't so great. I've seen for PbNO3 2. I've seen lead 1 nitrate. It won't be lead 1 because nitrate, there are 2 of them there. There are 2 nitrates, and so you're going to have to balance out both nitrates. For AgNO3, I've seen someone else say silver, nitrogen, and oxygen. Those are the 3 elements, but that's not the name of the compound. The compound is going to be silver nitrate. Silver nitrate. NO3, you must train your eyes to see that it's really one thing. It is one substance called nitrate. Yes, the elements are nitrogen and oxygen, and that's important to know. But together it is nitrate. So the thing will be silver nitrate. And other than that, pretty good so far. And I've seen. Oh, I saw one person say copper and silver nitrate. Um, that is not going to be a good answer. There is silver nitrate, but you can't just, factor out the nitrate, if you will. You have to say copper nitrate and silver nitrate, if that makes sense. Also, don't repeat any from the previous ones that you gave. So I will be looking at that, and once you start repeating yourself, then that won't be good. So there are 10 total things, and so I'm asking for 8, so it should definitely be doable. Just, give yourself some time to work on it to name it well, okay? All right. Now the last thing is the new thing. Sorry. Last thing I meant to say is that you should be getting some more questions either from this afternoon or tomorrow about wrapping up Unit 1. And so you'll want to pay attention and do those when those come out, during school hours, of course. Yes, that wraps up Unit 1. Unit 2 now. We'll be going through a bit more quickly. And we'll be looking at the nucleus. When the nucleus is around, you're going to have, well, the nucleus is always around. But when you're looking at what happens with the nucleus, you're going to be dealing with things like protons and neutrons. All the things that are before Chapter 25, regular chemistry, is with the electrons. So if we had been going on at a regular quick pace, this unit on nuclear chemistry would have fit between Thanksgiving and Christmas. And it's a very brief thing, and then the whole rest of the time since Christmas would have been on regular chemistry with electrons. But, with the COVID year, things have gone a bit more slowly. But the key thing here with nuclear chemistry is to understand that you're dealing with something that is very different from all the rest of the chemistry you're going to be dealing with. So protons and neutrons don't move around. They're just kind of there. And once in a while, the combination of the number of protons and neutrons isn't very stable. And we call different numbers of neutrons isotopes. So if I have, for instance, hydrogen, usually has no neutrons. But if I add a neutron, then it's twice as heavy, and it's called deuterium, deuter for 2. And if there are 3, then it's called tritium. And I should say 1 proton and 2 neutrons. And that is something that happens naturally but it's fairly radioactive, and you can make hydrogen bombs with it, if any of you are interested in that. We don't usually use tritium for hydrogen bombs, though, because it does decay fairly quickly. We use lithium deuteride, which is lithium with deuterium, and we can smash that together. It's a nice salt. We can smash it together with a regular atomic bomb, and that will force the nuclei together to make helium, which will be 1,000 times as powerful as a regular atomic bomb. Now, what do you see in the picture here?
Can you repeat that?
What do you see in the picture here?
Snow, ice, water.
There's snow, ice, water. I think you're missing the big thing. Yes? Big, long, tall thing, yeah. See here, see some people putting something in the chat here about submarine. Yes. Yes, that is a submarine, all right? And it is a nuclear submarine. You might see the flag there, right? The American flag. Probably they wouldn't have liked it if it were a Russian submarine, if we had, you know, taken a picture of it. And so, yes, there it is, the nuclear submarine. Now, it's called a nuclear submarine for two reasons. The engines use nuclear reactions to get the energy to move around, to go up, down, you know, forwards, backwards, and so on. And to purify the air and everything. And I have friends who have served in the Navy on nuclear submarines. You can't just go out and buy a nuclear submarine. Only governments have those things. But they've spent months underwater, never seeing the sun, and they take, you know, vitamin D supplements and stuff to stay healthy. But we've fairly well perfected the technique of living underwater. You can be down there for like 6 months at a time and live. Anyway, so that's reason number one. It's a nuclear submarine. Reason number two is because it also probably contains nuclear missiles, which just use regular chemistry to move from point A to point B. But once they arrive at point B, what do you expect will happen? Danielle? Quentin? Kayleen, what do you expect would happen when a nuclear missile reaches its destination?
It will go off.
Go off, what does that mean?
Like a missile is like a bomb, right?
Exactly, right. Exactly, it's a flying bomb. Yes. Exactly, yes. So in order to get from point A to point B, we could take bombs on planes, but those are slow and you can shoot them down. But when we perfected missiles to go between continents, we call those intercontinental ballistic missiles, then we were able to get things from one point to another very quickly. And, you know, this is a big worry back when there was a thing called the Soviet Union, because the United States and the Soviet Union each had like 25,000 nuclear warheads. Now we're down to just a couple thousand nuclear warheads each. The world is much, much safer now than it was when I was your age. Okay. So many, like 40,000 nuclear warheads fewer than before. Of course, that's still thousands of warheads, but yes, and you've probably all seen the possible consequences of that. Kind of makes COVID not really seem that big of a deal. But where does all this come from? Because we didn't have this 100 years ago. We did have submarines, but they were pretty bad. You couldn't be underwater very long, maybe a couple of days. We didn't have missiles at all. We certainly didn't have nuclear bombs. So where did all this come from? Well, there's a bit of history here. So when you go to the dentist might leave the room, or at least doesn't stand in front of the x-rays when you are getting x-rays through your body. to get X-rays through your body once or twice a year isn't a big deal to your body. If a dentist was there doing it a dozen times a day, all year long, they would die. And in fact, this is what happened with the first scientists dealing with radiation. Almost all of them died because, not instantly, of course, but after a few years of lots of radiation, their chemicals in their body fell apart. So, this. Yes, it was pretty ugly. And in fact, you could buy radioactive containers to invigorate your water, to give it energy, because they didn't realize it was poisonous. And one of the chief spokesmen for this, he would always go around and drink water from it, and it had more energy. But eventually his jaw fell off and he died. And so this was back 100 years ago. The Revigator, I think it was called. Nuclear water. So you don't want to mess around with this stuff. Radioactivity is all around us all the time. I love radioactivity. One of the 100 reasons I'm amazed that there's any life on Earth is that without radioactivity, we couldn't have life on Earth because we are too far from the sun to stay warm. We should have the oceans frozen over. And in fact, in some points in Earth's history, we have had all the oceans frozen over. That was a long time ago, way before the dinosaurs. But we shouldn't be warm enough because we're just a bit too far away to stay with liquid water. But we are warm because we have a superabundance of uranium and some other things in our crust that help keep us warm, that help keep the Earth warm. And we have a really oddly high concentration of these radioactive elements, like what we see in other planets we've explored, like Mars, Mercury, and other things. Earth is weird, okay? And anyway, so we've got a bunch of uranium, and so this is something that allows for life on Earth because it allows us to be warm. But there's so much more than that. So reactions differ from chemical reactions. So that's a big key question. And the answer won't be on the next slide. But as we go through the slides, we will see and build up the answer to this. So a little history. Becquerel was looking at photographic plates. And you know that if you take photographs outside, or I should say film outside, of the film canister, it exposes it. The light has made all the reactions happen, the chemical reactions happen in the film, and you can't use it to take pictures anymore. You ruin film that way. Nowadays, of course, we have digital cameras, but I think I saw that a local school, it may be Beloit, I don't know, has brought back film photography. Have you seen that in the news? With a dark room and everything. So where you can develop the film. There's like red light, which doesn't affect the film very much, and so you can see what you're doing. But you put it in this chemical bath, and it develops the film into photographs. Don't know? Okay, well, I think it happened. I didn't look it up to see exactly which school district is doing it. But anyway, so this chemical film normally would have a problem with sunlight, so you keep it in the drawer. But the uranium made the film unusable. It exposed it. But there wasn't any light. You could see no light. It was clearly dark in the desk. So what's going on? Well, with the help of the Curies, right, Marie and Pierre, they were able to get the idea out that these atoms were falling apart, and they were releasing energy. And as a result, radioactivity was discovered. So something's radiating, it's going out in a straight line. Activity, it's just happening, okay? There's stuff happening, it's not just sitting there, there's action. And uranium is the big famous one, but there were other ones, and she helped to discover polonium and radium, again named for being radioactive, and some other elements that eventually, once you hit lead, aren't radioactive anymore. So eventually, give it a few billion years, all the uranium will turn into lead. All right, so they come out from the nucleus. There are different isotopes that fall apart. And so again, different numbers of neutrons. Every element up until lead, let's say, or bismuth, has some isotopes, some number of neutrons, where it will not fall apart. It'll just sit there till kingdom come. But they have other numbers of neutrons where it will fall apart very quickly. And the way things fall apart, there are three ways they can fall apart. We'll get into tomorrow. But once they fall apart, then they are relaxed. They're not unstable anymore. But that release of energy can be good, can be bad. It can make people sick and kill them, like the Revigator guy, or it can help get rid of cancers. So, you know, it depends on what the use is, whether it's good or not. So the energy comes out. You can't affect it. You can't make reactions happen faster. You can't make them slower. You can't really control them, okay? But what you can do at the most is arrange the atoms so that when nature takes its course, you can make a chain reaction. You can help things along that they would normally do on their own. So why do they do this? Well, so that they can become stable. Reactions are always happening, whether they are electric, with the electrons, or they are nuclear. They're just always happening. And they usually go in an equilibrium back and forth, but you don't go from stable to unstable. So they just seem to happen in one direction for the nucleus. And we will start there with the types of radiation tomorrow. Thank you for coming. Tomorrow is the last of the everybody on Zoom. So I look forward to seeing a lot of you back in class in person on Friday, and then even more on Monday. Bye-bye.